Welcome to a new video about analog filter design. In this example, we will continue with the Chebyshev response. In this case, we will discuss a design of an active band stop filter. We will use again the Geffe algorithm to create a specific response for our filter design. And it will be an 8th order filter in this case. So we'll see how we can create this circuit using the Geffe algorithm. Of course, we will work out the calculations step by step and also verify these in SPICE simulations. Okay, we have the design objective. As said, we need to design a Chebyshev response active band stop filter. Using these specifications, we have a maximum passband ripple of 0.5 dB. The maximum or the minimum stop band attenuation must be 40 dB. And the effective gain at the passband, it's called midband, but at the passband must be 0 dB, so it needs to be unity. In addition, we have the lower and the upper passband frequencies, 200 and 750 Hz. The lower and upper stop band frequencies are 350 Hz. Okay, let's see how we can calculate the required component values for our filter now. Okay, our first step is the passband frequency, center frequency, and the quality factor from these two values. The passband frequency is the upper minus the lower passband frequency, which is then given here in Hertz, so we can calculate that also using this formula, and it will result in 2 pi times 550 radians per second. The center frequency is the geometric mean of the upper and the lower passband frequencies using this formula. When you substitute here the values, you will get here 2433.5 radians per second approximately. Now, taking these together, and the quality factor of our band stop filter must be then omega center over the omega bandwidth, which is then given here by 0.7042. Okay. We will use this value later in our calculations. Now, step 2 is the normalized passband frequency and the normalized stop band frequency for our prototype low-pass filter. As discussed in the previous examples, we always start with the low-pass filter prototype, and then we will convert that to the band stop filter in order to finalize our design. So this is the normalized passband frequency, capital letter omega p. This is always 1. You can also see that from the formula. And the normalized stop band frequency in this case is given here. You see also the stop band lower than the upper values. And that will give us in this case 2.75, all from the specifications. Okay, now this is an important step, which is then the filter order of our prototype low-pass filter. Now we need to convert our A max and A minimum to the scalar values. So this is given by the epsilon p, which is related to A max. A max is 0.5 dB. When you calculate that, you get this value. In a similar form for the epsilon s, using the A minimum, which is 40 dB, so we convert that, it requires 99.995, so almost 100. Now taking this together in the formula of the Chebyshev response formula for calculating the order, the filter order, and there it is then given by this formula, and when you do that, you get here 3.8026. Now we need to have an integer order, so that we need to go up to n is 4. So we need a 4th order prototype low-pass filter. This is not the order of the band stop filter we need to design. That will be discussed shortly. Step 4 is our normalized Chebyshev poles of the prototype low-pass filter. Now those are given by this formula. You see here the sine and the cosine terms, where the k and n is there. And you also see here the sine hyperbolicus and also the cosine hyperbolicus with a parameter a. So where k is the pole number here, and n is 4 in this case, because we have a 4th order prototype low-pass filter. And the a is given by this expression. You see here, again, the filter order n, but also the passband ripple as the scalar value. Now when you substitute here the values for 4 and 0.3493, we have determined in step 3, we get this value for the parameter a. Now we can calculate the poles. Now we have 4th order filter, so we will have also 4 poles, and those are 2 complex conjugate pole pairs. So those are given by this pole. So we have the K1 and the K4. Those are actually the pole pairs, and also the K2 and K3. So it's not like 1, 2, 3, 4. So you actually look at the mirrored version around the real axis in the complex plane. So those are the poles. Just look at this expression. You substitute here for k is 1. And of course, this will be then 4 for n, so that will be then divided by 8. And this a here will be then this 0.4435 in a similar form here, and then you go for also for k is 4, k is 2, k is 3, and you got these 4 poles. Now what do we do with these poles? Now we need to use these poles to come up to the final design of the band stop filter, but we know in order to go from the from the prototype low pass filter to the band stop filter, we need to make the inversion, pole inversion, go from the prototype low pass filter to the prototype high pass filter. Now pole inversion is really straightforward, as I said, so as the name implies, it is just an inversion of the pole. So you do 1 over what you have here. So this is given by here P1, 4 inverted, and that is given by this expression, and when you calculate that, you will have here the poles for our prototype high pass filters. In a similar form for the other one, k is equal to 2 and 3, again using the pole inversion, and you get these poles. So now these are the actual poles we need to use to convert to the band stop filter. Now we need to assign the Geffe poles. This is the algorithm we use, and we'll now have the Geffe poles for each band stop filter stage, which is given by G. Now the real part and imaginary part of each pole will be assigned to a Geffe pole parameter that will be then forming the Geffe poles. And the Geffe pole is given by this expression. You see here the capital letter sigma and the capital letter omega with the subscript G, which is then our stage. Okay, the index G as refers to the stage number of the final band stop filter. Now we have 4 poles. That means we have also 4 stages. So for each pole you make actually a stage. So the final band stop filter will then have 4 stages. Now each stage forms a second order filter. That means we have 4 stages times second order will be an 8th order filter. So n is actually 8 for our actual band stop filter. Now there is a note here, unlike the Bedford response band stop filter design, we do not scale the poles for the Chebyshev response band stop filter design using the Geffe algorithm. That was the case for the Bedford response. So then we need to go to the cutoff frequency normalization. This is not required for the Chebyshev response. So our actual required poles are these 4. Okay. So we have a band stop filter stage 1, which is given by G is equal to 1, which has the complex pole given by this. So you see the capital letter sigma and the capital letter omega for the stage 1. And then for the stage 2, that is given by the pole 4. So actually you take the complex conjugate of that one, and that is given by this one. You only have a change in the capital letter sigma, which is just a minus sign here. In a similar case for stage 3 and stage 4, you see actually here you take the P2 inverted and then P3 inverted. So pretty simple, actually you only make the minus sign for the capital letter omega. Now taking these all together, we now go to the Geffe parameters. This is the procedure we have also seen in the previous examples, and we'll now have for each stage the parameters. Now P1 inverted and P4 inverted forms a complex pole pair, so they are actually a group of 2 poles. So they are also having the same parameters for the Geffe. So they will be equal. They will also have the equal quality factor. They will also have the equal, we will see that short of the zero frequency. The only difference is the center frequency. Now, how does the calculation works out? Band stop filter stage 1 and 2, so that means G is equal to 1 and G is equal to 2. So we start with the parameter C1 given by this, so we only take the capital letter sigma 1 and the omega 1 from here. They will give you this value. Then we calculate the D1, which is then from here. You also need here the quality factor of the stop band stop filter. It was 0.7042, which is what was calculated at the beginning. Now we give you this D1. Now E1 is given by this formula. And then we have the G1, which is just a parameter. The important part is the quality factor here. Q1 is given by this. This is now the quality factor of the first stage. So 5.1688, and the K1 here is a parameter again related to the quality factor of the first stage and the quality factor of the band stop filter. Now the W, which is then given by this expression and this value, and we have now the center frequency of our first stage related to the W1 and the center frequency we have determined in the beginning. Now we have here 4604 radians per second as our center frequency of the first stage. And the zero frequency is equal to the center frequency of the original calculated value. Now we know that the second stage, so for G is 2, has also the same quality factor as mentioned here. So that means Q2 is equal to Q1, so that's equal to this, and W2 is also equal to W1. So what will it mean? That the center frequency here is then given by the omega center, so for the second stage, divided by the W2. So in this case, not multiplied by the W1 or W2, but divided by. That's the only change, as said here, the only difference is the center frequency. And this is now the center frequency for the second stage. Again, the zero frequency will stay the same. Okay, this is now for stage 1 and 2. In a similar case for stage 3 and 4, we look actually at this pole using the calculations. So we calculate now the C3 and then the D3, E3, really the similar calculations, and then G3. From there, the Q3, which is the quality factor of our third stage. And then moving on to the K3 and the W3. Now we calculate the center frequency of the stage 3 using the W3 and the center frequency here. That is then given by this, and this value 6020.6 radians per second. And we also have the same zero frequency as before. Now we also know that the Q4 is equal to Q3, as said before, because the quality factors are exact same for the complex conjugate pole pairs. And the W4 is equal to W2, so that's also equal to 2.4741. Now we can calculate also now the omega center for the stage 4 using this. So you now divide by the W, not multiply by the W. You get this center frequency, and this is again the zero frequency, which is the exact same as in the previous stages. Okay, now we have all the necessary information, so we can summarize that. Now this is the summary of the results. We have here the bandstop filter stages 1, 2, 3, 4. We see the quality factor for stage 1 and stage 2, which are exact same, and stage 3 and stage 4 also has the same quality factor. The only difference here is are the center frequencies. You see here the first and the second stage, third and the fourth stage. And those are all calculated here. So this is just a summary, and see also the zero frequency is exactly equal to the for each stage. Okay, now let's bring now the next step, which is our circuit realization. We will use the bandstop filter developed by James R. Bainter, and this is a second order filter. So for each stage we will create a second order filter, and this filter is given here. You see here that we have 3 op-amps, 2 capacitors and 6 resistors. So we need to cascade now 4 of this in order to create our final 8th order bandstop filter. Now we need to determine the magnitude scaling factor and the frequency scaling factor for each stage. Now we normally set the capacitor C1 and C2 equal to each other, so we just define it as C. We also set the R5 and R6 equal to each other, so that is just R, and this M is the gain, which must be unity, so it is normally that we just select it as 1. That means the R1 and R2 here will be also 1, so this is the inverting amplifier part in the beginning. Now this will result in a zero frequency by choosing this of each stage will be equal to the center frequency of the final bandpass filter. That means the omega z of each stage will be the omega center, which was actually calculated here. The frequency scaling factor of each bandstop filter will be equal to the center frequency of each bandstop filter stage using this formula. Okay. The magnitude scaling factor of each bandstop filter stage can be calculated using this. So you see here the relationship between the magnitude scaling factor, frequency scaling factor, and the capacitor value here. So if you choose a capacitor value, for example, you know your frequency scaling factor, you can calculate your magnitude scaling factor. The formula for the denormalized component values are shown here. You see here the R1 and R2, they are equal to each other. So again here the index G, which is related to the magnitude scaling factor. You can calculate here using this formula the R3, R4 is given by this formula, and on R5 and 6 is related at this formula. The Q here is the specific quality factor of the stage. So let's go for stage 1. So we select here the capacitor of 100 nanofarads. So each capacitor here is 100 nanofarads for stage 1. The quality factor for first stage was this, and we have also the center frequency 1, which was this. So this is now also our frequency scaling factor. From there, using this formula, we can calculate the magnitude scaling factor for the first stage. And that is given by this value, so 2172. Now using the formula here, you see here R1 of the first stage and R2 of the first stage is the Km, so the magnitude scaling of the first stage, which is then given by this. Now R3 also, using this information here, you see here, that will give us 752 ohms. R4 is given by this formula using the magnitude scaling factor and the quality factor. You see here the 210 ohms, and also the R5 and R6 using this formula. Now this is now 22.5 kilo ohms approximately. Now in a similar form, we use now the formulas now for the stage 2. Again, we select the capacitors 100 nanofarads. Quality factor is exact same as Q1. The only differences, of course, are frequency scaling factor, which is omega center 2, which was different. So that is also the magnitude scaling factor will be different. So the R1 and R2 will be then also this. So this will be also equal to each other. And then we can calculate also the R3 and also R4, R5 and R6. Exact same procedures before. I go now for the stage 3. The procedure is now pretty straightforward. You now take again the quality factor, the frequency scaling factor and the magnitude scaling factor for this stage. Use the formulas here given. You calculate now the R1, R2, R3, R4, R5 and R6. Also for stage 4 in the similar case. So those are now the values we have. First, the gain adjustment circuit. You might say, why do we need that? Now we have even ordered prototype Chebyshev response filter. So the required effective mid-band gain, let me start with that one, is 1, so which is 0 dB. But we have an even ordered Chebyshev response prototype filter. And we need, since we have that, we need a gain adjustment circuit that will make the A max, so this one, so minus A max, because this is a ripple, at the lower passband frequency and for the upper passband frequency equal to each other. So that needs to be adjusted in order to get that. That is always the case for even ordered prototype filter. So if you have NS2 or NS6, 8, doesn't matter. If you have an even ordered, you need to do this. The gain of this gain adjustment is then given by this expression, which is then 10 to the power minus A max over 20. So just conversion from the dBs to scalar value, which is then 0.9441. Okay, now we can realize this attenuation circuit using just a voltage divider. We can see that here, so you go in by A and then you measure at B. So we have actually here voltage division. In this case, we have an effective gain over passband gain. So at the lower and the higher frequency, since we have a bandstop filter of 1, that means we need to also use that. Now, let's take now, for example, this resistor 1 kilo ohms. That means we need to have this expression and then using 1 kilo ohm, for example, as the selected value. The AC here is 0.9441 and HM, which is in scalar value 1. So since we know what the RY is, we can calculate Rx, just rewrite this formula and you get this expression. We know what A sub C is, we know what the HM is, which is our mid-band gain or the passband gain, and that will result in 59.25 ohms. Okay, that means this is now 59.25 ohms. This is 1000 ohm, and that is now the required gain adjustment circuit after the 4 stages. The complete circuit is then given by this circuit in the SPICE simulator. You see here the first stage, the second stage, all of them are the second order Bainter bandstop filter. That will be then connected to the third stage and then fourth stage, and you see here the gain adjustment circuit. So in total we have a summary here. So R1, R2, R3, R4, R5, R6 and the capacitors, all of them are 100 nanofarads, and we see here the values for the gain adjustment circuit. Okay, now let's now look at the simulation result. This is the body plot for the gain only. You see here, first parameter is the maximum attenuation, which happens at 380 87.26 Hz from the simulations. Now we know that our center frequency was 2433.5 radians per second. If you convert that to Hertz, that will give you 387.3 Hertz, which is very close to what we have here. So this is a nice result. The next one is our passband frequency and also the gain. Now at 200 Hertz, which was our lower passband frequency, we have a gain of minus 0.5 dB as required. Okay. We also have at the upper, which is 750, so it is also minus 0.5 dB, so we go down by 0.5 dB. Now the gain here at 300 Hz, which is our lower stop band frequency, is minus 42.86 dB, which is more than 40 dB attenuation. At 500 Hz, you see here that it's exact same attenuation, so more than what we needed minimum for our stop band attenuation. So we can say all the specifications are met. But let's now zoom in this ripple part in more detail, because that part is critical, and also in order to understand why we need that gain adjustment circuit. So I just zoomed in the part where we have the ripple. You see here the two regions where we actually stop with a ripple and the part where we actually start with a ripple. You see here that the body plot gain actually started at a low frequency at minus 0.5 dB. That is required for even ordered Chebyshev response filters. And then we have increasing, so we have a peak here, a valley and a peak, and it goes down here again. And this part is at 500 Hz and minus 0.5 dB. If you don't do that gain adjustment, you will have a shift and it will be not correct. In a simple form, you see here at 750 Hz, you see here minus 0.5 dB, and it will goes also up and down in the similar frame. So this is an important part, and if you zoom in, you see that this is indeed the required circuit adjustment at the end. Alright, this was an example about the Chebyshev response for an active bandstop filter, which was an 8th order filter. We have used our Geffe algorithm to design our circuit parameters. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your support and cooperation, and see you next time in another video. Take care.